Let's start solving the exercises. Our first exercise set. Today we are going to solve only exercise 1 because it has several parts. So in this exercise, a set will be given. In each part, a set will be given and a relation will be given on that set. We have to say whether the relation is reflexive, symmetric and transitive. And the first one is this. So here, the set is the set of all positive integers less than or equal to 14. That is the set A. And this R is a relation on A. This means that the X and Y are coming from A. They are elements of A. And X is related to Y if 3X minus Y is equal to 0. Is this relation reflexive? Let's see. You can write the sentences, the language, everything yourself. Let us just see the mathematics. For the relation R to be reflexive, x comma x has to belong to R for every x in A. That, however, is clearly not true because 3 times 1 minus 1 is equal to 2. That is not equal to 0, which means that 1 comma 1 does not belong to R. So R is not reflexive. Not reflexive. Next comes symmetry. Note that 1 comma 3 belongs to R. Why? Because if you substitute x equal to 1 and y equal to 3, then you really get 0. But is 3 comma 1 in R? No, it is not. Because if you substitute x equal to 3, 3x becomes 9. 9 minus 1 is 8, that is not 0. So this ordered pair is in R, but the other one is not in R. So it's not symmetric. What about transitivity? For that, let us consider this. We already know that 1 comma 3 belongs to R. So let us also note the fact that 3 comma 9 belongs to R. Both of these ordered pairs belong to R. If you substitute x equal to 3, then 3x becomes 9 and 9 minus 9 is really 0. So 3 comma 9 is in R. But what about 1 comma 9? Is that in R? No. Why? Because 3 times 1 is just 3. 3 minus 9 is minus 6. It's not 0. So the relation is also not transitive. So it's neither reflexive nor symmetric nor transitive. Second one, the set on which we have the relation is the set of all positive integers, natural numbers. So our x and y are natural numbers, any natural number. And the relation is this: x is related to y if y is equal to x plus 5 and x is less than 4. So few possible values of x are there that we can write this relation in tabular form. Let us do that, okay, and see which ordered pairs are its elements. Because x is a natural number, its smallest possible value is 1. When x is 1, y is 6. So 1 comma 6 is an element here. X can be 2 also. Then we have this ordered pair as well in R. And x can be 3. This is the only other value of x. In that case, we get 8. So this is the relation. Is it reflexive? No. Why? Because, for example, it does not have 1 comma 1. that is why it's not reflexive. Let me just adopt a shorthand notation for for writing whether it's reflexive and or symmetric and or transitive. What I am going to do, I will write like this, okay. Reflexive, symmetric, transitive. It is not reflexive means I will strike R. If it turns out to be symmetric, I won't do anything to S. Otherwise, I will strike it. And similarly for T. And let me write this thing here. Okay, so for our relation, we have already seen that it's not reflexive. So I strike R. What about symmetry? It has 1, 6, but it does not have 6, 1. So it's not symmetric. What about transitivity? Be careful. Transitivity says that if x, y and y, z both belong to R, and then that implies that x, z is also in R, then R is transitive. Can you find any ordered pairs which you can take in place of x, y and y, z here? No, because for example we have 1, 6, we do not have 6, something. Okay, so this implication in this situation does not have any hypothesis. The left side, that statement is the hypothesis of the implication and the right side is the conclusion. So we do not have any hypothesis means the hypothesis is not there or it's false. That is why the implication is vacuously true. But true nevertheless, and that is why it is in fact transitive. Okay, it's not reflexive, it's not symmetric, but it is transitive. Here the set is this, all the first 6 positive integers, and the relation is this, x is related to y if y is divisible by x. Okay. Now obviously this relation is reflexive because no matter what x we choose in A, x is divisible by x. So that is why x, x belongs to R. Note carefully that the fact that there is no 0 plays a role here. Nothing is divisible by 0. So but however, every non-zero integer is divisible by itself. That is why the relation is reflexive. So R persists, R is there. Is it symmetric? No, it's not symmetric. For example, 1, 2 belongs to R because 2 is divisible by 1, everything is divisible by 1. But 1 is not divisible by 2. 2 does not divide 1. So 2, 1 does not belong to R, and that is why it is not symmetric. What about transitivity? Transitivity is in fact present for the divisibility relation. Why? Let's see. Say x, y and y, z both belong to R. This means that y is divisible by x and z is divisible by y. But then obviously z is divisible by x, and that is why x, z belongs to R. So it is reflexive and transitive but not symmetric. Set is the set of integers and this is the relation. It relates the integer x to the integer y if x minus y is an integer. Now it's a very general relation. I say general because it's the largest possible relation in this case. You take any two integers, their difference is always going to be an integer, and that is why this relation relates every integer to every integer, including itself. And that is why this relation actually is the entire set z times z. Will it be reflexive? Yes, of course, because everything is present here. In particular, this is present for all x belonging to z. So, reflexive. Is it going to be symmetric? Yes. If you consider x comma y in R, then y comma x is also in R, because everything is in R, and that is why it is transitive also. If these ordered pairs are in R, then so is x comma z. So this is a reflexive, symmetric and transitive relation. It's an equivalence relation. Although it's a very boring equivalence relation because it relates everything to everything in the set. So if you remember, this is actually the universal relation on this set, the other extreme opposite of empty relation. Actually, there are parts of this fifth one itself, but in all of them, the set A is the same. A is the set of all human beings in a town at a particular time, or more accurately, in a given period of time. At a particular time doesn't mean at a particular instant of time, of course. And the first relation on A is this. So x and y are coming from A, that means they are two persons. They are related if x and y work at the same place. A little inspection reveals that this is actually an equivalence relation. X and x obviously work at the same place. If x and y work at the same place, then y and x also work at the same place. And if x and y work at the same place and y and z also work at the same place, obviously x and z also will work at the same place. The idea here is that they work only one job. Okay, y simultaneously doesn't work two jobs. Simultaneously means you get the point, what that means. Some people work two jobs. Say in the morning they work one job and then in the evening they work another job. It's not like that. So that is why the relation is reflexive, symmetric as well as transitive. So it's an equivalence relation. Y are related if they live in the same locality, and arguing just like that previous one, you can clearly see that this is also an equivalence relation. X and y are related if x is exactly 7 centimeter taller than y. Obviously, this relation is not reflexive, because x cannot be taller than themselves. Can you be taller than yourself? No, that too exactly 7 centimeter. That's not possible. It is not symmetric either. Say this is x and this is y. So x is 7 centimeter taller than y. Can you then simultaneously have y 7 centimeter taller than x? No, y is shorter than x. So it's not symmetric either. What about transitivity? If x is 7 centimeter taller than y and y is 7 centimeter taller than z, is x 7 centimeter taller than z? No, 14 centimeter taller than z. But then x and z are not related. That is why it is not transitive either. So it's a very bad relation when we are looking at relations from the point of view of equivalence relation. It's none of this, reflexive, symmetric or transitive. Okay, so next we have this somewhat hilarious relation. Relation is not hilarious, but what we are going to do with this will be somewhat funny. X is the wife of Y. Can it be reflexive? X, of course, cannot be the wife of X itself, right? So obviously it's not reflexive. Is it symmetric? No, it cannot be symmetric either. If X is the wife of Y, how can Y then be the wife of X? That is also not possible. So it's not symmetric. Who said these questions, man? But anyway, however, it is transitive. It is transitive vacuously. Let's see how. This is the condition for transitivity. Is the hypothesis of this implication true? No, the hypothesis is not true. You cannot have two such pairs simultaneously in R. Why? Because this pair being in R means X is the wife of Y. But then how can Y simultaneously be the wife of someone else? Because Y is male, right? So the hypothesis is false. So that means whatever the conclusion is, we need not worry about that. This is vacuously true. So somewhat strangely, it is actually transitive. If, however, you are thinking of same-sex relation, then it changes. But I am sure that the authors did not mean that. Okay. So in our traditional type of relations, this is in fact vacuously transitive or just simply transitive. And this is the last one. I think someone did this intentionally. I mean, you just look at it. X is the father of Y, right? So now you think of reflexivity. Can you be your own father? Of course not. So this is not reflexive. What about symmetry? If X is the father of Y, of course, how can then Y also be the father of X? Not symmetric. What about transitivity? If X is the father of Y and Y is the father of Z, then again, how can X be the father of Z? X will be the grandfather of Z, right? So it's not transitive either. So it's again another such bad relation. I am not saying that the relation between father and son or daughter is bad. That's not what I mean, okay. I mean, from the point of view of equivalence relation, it is really bad that it's none of these three. So on that hilarious note, this video ends. And tomorrow, of course, we have another upload. So see you tomorrow with whatever it is. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.